Before I invite you to our speakers and introduce them, I'm just going to go through the agenda and a few kind of house rules, I guess. So we'll have the introductions, and then Witekio will kind of take the stage for their masterclass. And you can see exactly what they're going to talk about in the top here. Then Mender will do the same, and you can see exactly what they're going to be mentioning here. There'll be a very short overview of how Witekio can help you if you're struggling with any embedded software problems. And then there'll be a live Q&A. If you're watching on live stream, hello. You can take part in our polls, which are down in the corner here, and they just ask you kind of how familiar you are with Yocto so that we can gauge kind of what audience we're talking to. You can also ask questions in the chat. They're completely anonymous, so don't worry, your name won't be read out. If you are joining us on LinkedIn, on YouTube, or on Twitter, hello. You can also ask us questions and comments, and we'll get those through as well. So at the very end, I'll be going throughout the whole event and kind of collating the questions, and then I'll ask everything at the end. Okay, so let's get started. Joseph, can you please introduce yourself and tell us a little bit about you?
Hello, everybody. Thanks, Witekio, for inviting me again to this second iteration of the masterclass. My name is Joseph. I'm serving as head of developer relations with Mender, which essentially means I've taken my passion for teaching about the Yocto project and embedded Linux into a full-time profession. And this event here fits in nicely, so welcome on board.
Okay, and now Nick.
Hi, everyone. My name is Nick. I'm one of the embedded team leads at Witekio. And over the years, I've worked on a wide range of embedded Linux and microcontroller projects across various market sectors, from board bring up and device drivers through to libraries and applications.
Amazing. Okay, Nick, if you'd like to kick us off and then start the Witekio masterclass.
Sure thing. We'll start with kind of a higher level look at the various parts of Yocto and how they relate to each other. And then we'll take a deeper dive into variables and overrides and a bit of a practical application of how these are used to integrate Mender. So what is the Yocto project? It's a collection of tools and scripts for creating custom Linux distributions, which are kind of targeted primarily at embedded devices. It's an architecture agnostic, so you can generate a distribution for a very broad range of products and on a wide variety of silicon. And with Yocto, it's possible to maintain a single code base that you can share across your entire product line. So some other useful features of Yocto include its ability to be able to generate package manifests for your images, including which licenses are applicable to those. So kind of a software bill of materials. And then you can also get it to restrict particular usage of packages that are subject to a particular license. So for example, the GPL v3, it's got a strong copyleft license. And you can also get it to build an SDK that you can install on another machine for application development. So that SDK would contain the cross toolchain and all the libraries which are tailored to your specific image. And another thing which is really a useful feature is that you can get it to perform basic CVE checking, like common vulnerabilities and exploits, for all of the packages that you're using. So the Yocto project contains and maintains various tools and components, including Open Embedded and Pokey, which you may have heard about before. So Open Embedded consists of Open Embedded Core, which is kind of metadata of foundational recipes and classes and associated files, and BitBake, which is kind of the build engine at the heart of the project, really. I say it's maintained by the Yocto project. It's co-maintained by the Yocto project and Open Embedded. And then there's Pokey, which is a reference distribution. And although that's not production ready, it's a good starting point for you to do your customization from. And then the Yocto project also contains various other layers and production tools and development tools and things as well. So a lot of the power of Yocto, and the reason it's able to do the things we kind of mentioned a minute ago, is because of metadata. So metadata is a real key element of the Yocto project, and it's contained in files that the build system parses when building images such as recipes and classes and configuration files, and various other information referring to the build instructions themselves. Essentially, it consists of tasks, which are like a bunch of instructions, and variables. And then this metadata is logically organized into layers, which are also known as meta layers. So layers are, as we just alluded to, layers are repositories that contain a collection of related metadata. So you use these different layers to logically group and separate information in your build. For example, you could have like a BSP, a GUI layer, a distro configuration layer, middleware, and application layers, for instance. And these layers are hierarchical in the ability to override previous specifications. And the way that's achieved is by each layer having a priority. And in that, the higher the number, the higher the priority of the layer. So you can basically take any number of these layers from the Yocto project or various other sources, and then you can add your own custom layers to this as well to build your overall image. So let's take a look at the anatomy of a layer. Here we can see a recipe and a recipe append file. So these things are conventionally organized within recipe group directories inside of your layer, and in the recipe core one, as it shows in this example here. And these recipes contain tasks and variables for building the packages, which are then ultimately kind of combined to build your binary image for your device. And they describe where to get the source code, what version of it you need, which patches should be applied, and how to configure and compile and install it. And then the recipes can be amended or modified by using bb append files. So we see this recipe append file here. And we'll look at how those work a bit later on. Spot the deliberate mistake in this slide. So this isn't a recipe, this is a class. So we can see a bitbake class here, and these are basically contained in a classes directory, and they abstract common functionality that can be utilized by multiple other recipes. So some good examples of this are the CMake or AutoTools classes, and they implement all of the tasks for building software that use one of those build systems respectively. And to use one of those classes, you simply inherit it in your recipe. So you can get a lot of the heavy lifting done kind of for you. Also, similarly to recipes, they contain both tasks and variables. Next, we're going to talk about configuration files. These hold global definitions of variables and user-defined variables and other hardware configuration information. And they tell the build system like what to build and put into the image that we want for our particular platform, our particular device. So there's different types of configuration files. And in this slide, we can see there's a distro layer on the left and a BSP layer on the right. And there's a slightly different directory structure which is used. And there's some distro-specific and machine-specific variables which are contained in those configuration files that make them of that type. So unlike recipes and classes, configuration files only contain variables, although you can use some scripts as part of the variable assignment. But there's also include files. So these are similar to including header files in, say, C or C++. These can typically contain a number of variables as well. And there are other files as well. So these can be things like patches or auxiliary files that are used to fix bugs or customize the software for your particular situation. It might be like resource files to install on the target root file system and the likes. So if we take a look at how the various types of metadata relate to one another, we can see that recipes can include 0 or more other files by using the include or require keywords. And the behavior of these two keywords differ in that included files, if an included file can't be found, then require will cause bitbake to generate an error, whereas include won't. Recipes can also inherit multiple classes, which, as we can see in the diagram, can themselves inherit multiple classes and include files potentially. And classes are inherited from within recipes using the inherit keyword. What's the difference between inheriting a class and requiring an include file? Some small details really, but one of the main differences is that you can conditionally inherit class files by using overrides, which again we'll talk about a bit later on. Recipes also often have other files such as patches. You can see in the green box, the kind of greeny blue box here. And these will be applied during the do patch task for the package, or as we mentioned earlier, resource files that might be installed on the target root file system. They're accessed using variables inside of the recipe rather than a keyword. And finally, these recipes can be modified in other layers with higher priorities by using BB append files. And they can be applied to either specific versions of a package, or they can be applied to any version of a package by using wildcards. This image here depicts the relationship of metadata files to configuration files. As you can see, there's a lot of similarity between the two, but a key difference is their scope. So whereas recipes are local and they can't affect other recipes, configuration is global. And configuration files are parsed before recipes and BB appends, which we might touch on a bit later on. And if you want to inherit classes from a configuration file, as opposed to a recipe, then it's done by extending the contents of the inherit variable. So this diagram shows some different examples of layer composition using BitBake. And we'll kind of break it down and talk about them briefly each. So here, the recipe in layer 4 is going to be used unaltered in the final build configuration below the kind of black line, because it only exists in that one layer. And similarly, the recipe in layer 1 here is going to be unaltered in the final build configuration as well. And for layer 2 here, it's the same. Here we have something a bit more interesting. This next example, there's a base recipe in layer 3, and then that's been amended by a BB append file in layer 4, which is higher priority. So that BB append file would typically add or extend or change the variables in the base recipe from layer 3 in this case. But it's also capable of adding or modifying the tasks that the recipe performs too. So it might do like a custom install task or various things. It's very flexible. Okay, and now in this example, note that both the files are BB files. There's no BB append file here. So here, the recipe in layer 1 is completely superseded by the recipe in layer 4, which is higher priority. So the version which will be in the final build configuration will be the one from layer 4. And in this example, we have a base recipe in layer 2, which has been amended by a BB append file in layer 3, which is then further amended by a BB append file in layer 4. So the BB append file in layer 4 might modify the variables and tasks in layer 2 or layer 3, or it could modify them in both. Or it might not modify them in either of those layers, and instead it might just add some new variables or additional patch files, for example. As I said before, it's really quite flexible. And this final example just shows another recipe being amended by a single other one. So here we've got layer 1 being amended by a BB append file in layer 3. And an example of this could be kind of a recipe in Open Embedded Core, which is then modified by a BSP layer, for instance. A thing to note is that the layer priorities only work for recipe metadata and not for configuration metadata. So from configuration metadata, another mechanism comes into play then, and that's use of the BB path variable, and that's kind of organizes the layer path order very similarly to the path environment variable in a Linux shell. So some other key kind of Yocto terms are image, machine, and distro. An image is basically a recipe that pulls together all the packages that should be installed in your binary Linux distribution. And when building an image, you specify the machine and the distro variables either through the local configuration file or through environment variables, typically. Machines are defined in the BSP layer. Machines define BSP layers, and they contain machine-specific configuration. And the machine variable specifies like the target hardware of the machine that we're trying to build our image for. And distros are defined in distro layers and contain policy configuration. So the distro variable specifies what build configuration policy that we're going to build for our image. It includes things like which libc that we're going to use. So combined, the machine and the distro, along with some other related variables, influence what's built by a number of other recipes that are pulled in by our image. So finally, I'll leave you with a couple of tips for creating some layers. And those are, don't copy an entire recipe into your layer and then modify it. Just use a BB append file to override just the bits of the recipe, of the original recipe that you want to modify. Avoid duplicating the include files from one layer into another. If you've got a recipe that does need to use an include file from another, then you can use the relative path to that original layer. So in this example, require recipes core package file.inc instead of just require file.inc and it being copied into the local directory. You also want to be like the cool kids, follow the naming convention, the layer naming convention, and clone your repositories alongside other layers in the source directory. And if you have any, where you have any machine-specific files, you want to place them in a machine-specific location within your layer. So this basically means that you're not going to end up with wrong metadata as you kind of share this with other builds and other images. You don't want to have like bad metadata being pulled in. So if we take my very unimaginative example here, we have a custom layer called meta custom and a machine called custom machine, and we're going to be appending the base files recipe. So we create an appropriate directory in our layer and put all the files which are specifically for our machine in it. And then in our appended recipe for base files.bb append, we prepend the file extra paths variable. So that way it will search for our specific overridden files before it finds any of the base recipes once in its layer. So that's it from me. Thanks for listening. And now I'll pass over to Joseph, who will dive deeper into variables and overrides.
Thanks a lot, Nick, for covering all of the whole picture, because this is what you will need in order to dive into the details. Let me head over here. Yeah, you've had a short introduction about me. This is mainly here for your future reference and for the lovely picture of me, obviously. And now let's go to the good stuff. Good stuff means we want to make real products, and real product mean we need to have an understanding of the whole thing. And now we've understood the whole Yocto, so we need to take one step back, understand what over-the-air updates, because that's what Mender does, actually mean, and then we will put this all together, making the combination beneficial for your actual work. So in order to do an over-the-air update, what is the first and foremost thing that you should want to have? Is it should be fail-safe. It should be robust. In developer lingo, it should never brick your device. We might like bricks for building houses, but actually it's not really cool if you have an piece of expensive electronics on your desk or even somewhere in your fleet that is as useful as a brick because it doesn't run anymore because you've ruined the software. So this should be avoided at all costs, even when losing power at very unfortunate points in time. How can that be achieved? The update mechanism should be capable of doing the update in an atomic manner, so you never end up with only half of the update being deployed. Of course, when deploying the update, it should be verified that it's integrated, that its integrity is okay. It has not been corrupted either by an attacker or bad events by some bit flip in a transmission. And taking this one step further, if your requirements do so, then you will want to have a form of code signing. That means only the software that you specifically have provided will actually be accepted as an update. We have talked about robustness, and what does this now mean under the hood? Usually, one of the main mechanisms to achieve this is the AB system update scheme these days. This means you have an active partition and an inactive partition. The active partition is the one that is currently running, that is in operation, and when an update arrives, a system update, it is being deployed to the inactive partition. And only once that is completed and verified, there is a reboot. The bootloader flips active versus inactive, therefore now putting the previously inactive partition into use. And if everything works fine, it comes up again. It can check, say, okay, operational stage reached again. The update is committed. Everybody is happy. If something bad happens along the way, well, so your watchdog will kick in, a reboot will kick in, somebody will turn it on and off again, and the bootloader will need to realize that, oh no, we didn't manage to make all the way to the finished update, so something bad must have happened. I'm flipping back to a known good operational state, and then we can see and proceed from there. You can already understand that there needs to be a bootloader. There need to be at least two partitions, and with the flipping happening, that essentially means that both of the active and inactive partitions are completely transient. They can be replaced at any point in time. So at least for a configuration and probably also some of your logs and process data, whatever, you will need some additional means of persistent data storage. So usually your storage layout will look something like this. And as simple as the diagram is, it actually means there is a lot of stuff to configure. What is the state device, for example, first and foremost? Then the bootloader, it's not exactly a trivial piece of software. It usually needs quite a bit of configuration. Then the partitions, A and B, what is their size? What file system are they using? And last but not least, the persistent data. Should there be some preloading? Where in the system should it end up? Is there more than one persistent data partition? These are all things that need to be properly configured for your specific application. And how does one put configuration, which is a form of information, into a Yocto project build? Nick already covered it. It's metadata. Metadata is the key technology in the Yocto project, and the building blocks of anything metadata are variables. So we will now really look at what variables really are and what they mean and how we can work with them. Technically, and here comes like the short history lesson here. All of the variables end up in your build environment for whatever thing that you build as environment variables. This is stuff that goes back 20, 30, 40 years in some places because it really lives in the Unix shell. This comes from makefiles that used to be the prime means to actually build software. and a lot of stuff in there was hard-coded, which was not good. So people devised like convention that specific bits and pieces in the makefile would not be hard-coded, but if they existed in the environment, in the variable, they would be pulled in and used instead. This would first and foremost be the compiler, which is hidden behind the CC variable usually, but also flags that can be passed to the compiler, flags that can be passed to the linker, and all of kinds of stuff that you can even imagine. So this is what variables end up as for your specific task that you are actually executing during the build time. And now we're going to do the jump back to real Yocto code. How does one operate on variables? This is a small demo recipe which I will be using for the first block of explanations and operations that we will be talking about. These are I call them like arithmetic operation, and that's why I picked that fancy colored icons over there. The first block, A1, is like appending, as the name already gives away. A2 is about prepending, and A3, the shorter one, and I will tell you why, is about removing stuff. You can have a short peek at the operators here. There's a plus equals and equals plus. There's a dot equals and equals dot. There's the colon plus command syntax, and there's obviously assignments. So look at this for 1 or 2 more seconds, because now we're going to talk about it. This is A1. In a Yocto build that is properly set up, you can inspect the whole evaluation history of a variable using the bitbake getVar command. In this case, everything is in the demo recipe, and we want to look at the A1 variable. So bitbake getVar -r demo A1. This is what we want to see. And the listing looks just like the recipe that I've just told you. It goes from top to bottom, A, B, C, D. But now you can see that the operators are like reworded and more verbose. There's the colon append, which I just called a command. This is not exactly right, but I will tell you in a second why. Then there's the append and the post dot. What does append and post dot mean? Append means this is adorned with spaces and appended to it. Post dot means it is not adorned with spaces and slammed directly onto the variable. And then the colon, which means this happens in the expansion variable stage. Why is this important? You look at the order and it should be like A, B, C, D. And then you look down there and it says, why is it not A, B, C, D? That's the reason why. A is not a colon operator. It is the setting or the assignment that is perfectly clear. Colon append, it happens later, so we gotta skip it. Append C, that's the one with the spaces. So A space C, post dot, no space, A space CB, and then finally comes the colon operation. B is appended. Now that makes actually sense. When do you actually need this kind of operation? Each and every day, because this is the most common kind of operation whenever you do anything in Yocto. You will usually always extend variables because this is the core mindset of Yocto and Open Embedded. Start out as minimal as you can, and then add and add and add and add as fine granular as I can and as little as you actually need in order to achieve your aim. So the classic example, if you are just starting out, you will probably extend image install. Nick has already mentioned it, the image that pulls stuff together. This is the core variable that defines what actually goes into the image. You will add stuff to it in order to get it into your image. So if there's only one operation that you can memorize for the Yocto project, then this is it. You can then, if your brain can only take one operation, close your ears now and keep that one. So now we're going to the more advanced stuff. Nick already mentioned the BB append. BB append means when Yocto evaluates, bad me, first explanation, then reasoning. Yeah, I'm getting carried away because I talk about this stuff a real lot. And I sometimes forget about the clear line of reasoning. But again, I've covered the operators. Again, this time it was the equals plus, equals dot, and colon prepend command stuff. Technically, it works just the same, but it works the other way around. Everything is not slapped to the back of the variable, it is put in front of it. And as we've already discussed the order of the evaluation, now you can easily guess why it looks like BDC space A at the bottom. And now I apologize for my bad line of explanations. This is where you actually will need it in your BB append. Your BB append is technically appended to a recipe, but you often will need to overwrite stuff in it, which means stuff needs to be applied before the actual recipe kicks in. And the first and foremost, these are configuration files that you will need to prepend and therefore overwrite. And Nick already had it hinted a little bit. Files extras prepend, files extra pass prepend to pick up your overriding configuration files. This is the place where you will need prepending. Third and most rare operation is removing. I already told you that there is no minus equals or equals minus operation. That's because removing is only possible in the second stage, and it keeps the spaces. When do you actually need it? Hopefully not at all. I told you it is actually like contradictory to the mindset of starting out small and adding, but there are like people who do not really stick to those principles, which means they add a lot of stuff and then hand it over to you, and you get to pick up the mess and say, but I don't want all of this stuff. And if you get such a kind of set of metadata that you cannot just modify because it's like an upstream thing, then colon remove can be your last means of actually properly working with that data. So we've covered operations now. And the second part is actually super simple. It's only about assignments. But assignments and defaults. Again, there's one example, A4, which overrides the default, A5 that just keeps the default. This time, as there are so little actual operations, I've just kept the evaluation on one slide. You can see in A4, even though the defaults assignment was below the real assignment and BitBake evaluates from top to bottom, the assignment of A took precedence because default is like a weak assignment and it only kicks in if there is no hard assignment. And for A5, there was no hard assignment. So the weak assignment, denoted with a question mark here, kicks in. When do you actually need this? If you provide metadata to your downstream users where it makes sense to be able to actually override this. Where does this happen in real Yocto? First and foremost in the local.conf, where download dir, the elder, and state are either commented out or assigned by a default operator, which means you can pass them in through the environment, therefore pointing it to arbitrary locations on your machine, but without having to actually modify the metadata. Now we are coming to the third and probably most fine granular means that you have working on variables. It's overrides. I just nicknamed the commands, which is actually not true. De facto, they are overrides. That this is BitBake lingo for the second evaluation stage. This can be the append and prepend stuff. They are technically implemented as overrides. But when somebody says override, they usually mean machine or distribution. And now, what does it look like? Again, a demo. A6 is assigned A, but A6 : Pocky is set to B. And again, for this is obviously a distro. Now we're gonna look at the machine 2, A7, same thing, but for the Raspberry Pi 4. We'll look at the evaluation. And now the term override actually shows up, and it tells us when Pocky kicks in, the value of B takes precedence. When do you actually need this? When you're building and you have some setting that enables your code to kick in with debug functionality. You might want to kick this switch in, not in production, but only if you're building your debug distro. So you would have an operation in your recipe that goes like append minus d debug or debug equals 1 or whatever to your makefile invocation or build system, but only if you are building for the specific thing that you might call Pocky debug or whatever. And in each and every other case, nothing happens. You can ship the production code. So this is often used in combination with an appending operation, not actually replacing, but appending. And more common in my understanding is overrides per machine. Distro and machine are the two things where you can actually override stuff. And machine is one that you will probably often need, because in a machine usually introduces hardware dependencies, and your code will often, as we are talking about embedded, will often need to react to hardware peculiarities. So if you're building for hardware A, you need to fine-tune this thing. If you're building for hardware B, you need to fine-tune another thing. And inserting those switches without cluttering it in your own code, for example, this is a perfect way to use machine overrides. And you might get the click now why I've put that last and introduced the Mender configuration first, because this is how you can actually put it to work. I've mentioned the boot partition, which is usually a default of 16 megabytes. But this does not work for every hardware. Specifically, the Raspberry Pi, for example, brings a lot of stuff that needs to go to the boot partition, so it will fill up much faster. You will not be able to actually build the image. Therefore, you need to reserve more space for it. But if you are building for multiple platforms, you probably do not want to affect the other ones. So you will want to set this variable only for the Raspberry Pi. And this is how you do it. You use a machine-specific override for the Raspberry Pi, setting it to 64 megabytes. And see, you've perfectly fine-tuned your build using Yocto variable operations. And that's why you really should have a good understanding of what actually happens when you need to do stuff, or what happens if you read such stuff. With that, a short conclusion on my end. Mender can be easily integrated into Yocto build with MetaMender, but we know that configurations or customizability is really crucial in embedded. This is not that like everything looks and feels the same. So we have a lot of variables exposed that you can fine-tune and use exactly in this way. And if you really know what you're doing, if you have a good understanding of variables, this will greatly enhance your maintainability and also your development flows. And with that, if you want to know more about Mender, it's super easy to get in touch with me and us and everybody. Here's just some ideas how you can do so. I'm happy to take a lot of questions, hopefully by now. Thanks so much. And back to my fabulous hosts. Thank you for having me.
Thank you so much, Joseph, and thank you, Nick. You're grand. A little change of setting, but that's all good. Everything's live. It's got to go perfect. So just very quickly, let me talk about how Witekio can help you. We've had some people in the chat asking us. It's not going to be a hard pitch. It's just very soft. So obviously Witekio is your on-demand IoT partner, which means we can help you bridge your skill set gap, we can accelerate your time to market, and we do a host of different options and services and software services. So it's not just about Yocto, we can help with migration or connectivity or optimization. And we work with a lot of great partners like Mender, and we're official partners. So it's perfect. So if you want to contact us even for a workshop and not a full project, we're here to help. And thank you again, Joseph and Nick, for helping. Obviously, now we're going to go on to the questions. We've had some great questions come in. So thank you to everyone who's already done that. And we've got people obviously on YouTube as well, which is very exciting. So the first question came in and it asked, can you give examples of which layer might be, of what each layer might be, sorry, like layer 1 being BSP, layer 2 being build?
Nick, you want to take it?
Sorry, Nick, you're on mute.
It helps if I unmute, doesn't it? Yeah, sure. So my example was a little bit artificial in order to just kind of convey what was going on. But so in reality, let's say Metapoki has actually got a layer priority of 5. And that's kind of like in the, let's use a real example. So on the Raspberry Pi, it uses Metapoki, and that's layer 5, and that's the lowest priority layer that there is. And then they're kind of just all used relative to one another. So there's not kind of a hard and fast layer 1 needs to be this, layer 2 needs to be this, layer 3 needs to be that. So it's not like core, so kind of like base, BSP, multimedia framework, application. It's not like that. You can kind of slot them around, and there can be gaps between those priorities as well. So yeah, taking Raspberry Pi, the BSP layer containing kind of all of the machine configuration is at layer 9, for instance, and there's a gap between kind of 7 and 9, but there's I'm kind of waffling a bit here, but
it's fine. It's fine.
Hopefully that makes sense. If you've got like kind of, if it doesn't, or if you've got any follow-up questions, please post it to us, and happy to answer it more specifically.
Okay, perfect. And then Joseph, maybe you could take this one. So someone asks, when we build a target image, the root file system has weird timestamps for objects, e.g. the date is 1970 or a bunch of other dates. Could timestamps of all object on rootfs be set to the time of building Yocto, i.e. could it be configured in some recipe?
In a recipe, certainly no, because the recipe would mean that you have to affect all of the build, and that's what a recipe just can do. A recipe is always local. I don't know if there's already some magic in there, which is very well possible, but I've never hit that instance. And for the silver bullet, there's something that's called rootfs postprocess command, which should be able to do essentially all of this, like find each and every file, do a touch setting the file stamps on it, and be good with it. So if there is nothing in Pocky itself or Open Embedded itself that you can easily find, then this is a classic case for post-processing the rootfs, and there is a mechanism for that.
Okay.
Yeah.
And question.
Sorry, just going to add, it depends what you're trying to achieve, really, because obviously those timestamps would only be still set to whatever your build time was, rather than the time that the device is going to get kind of provisioned with that root file system. So if it's just that you want to find out what the timestamp was of the build time, then you can access that in the Yocto rootfs under etc timestamp as well.
Okay, cool. And question 2 from the same person, they must have been very enthralled, how lovely, which it was, when an embedded system is connected over cellular, data traffic costs money. Is there a way to reduce update overhead?
Well, I guess that goes to me too. Compressed delta. Delta compression is sometimes problematic because it massively varies on the kind of data that actually is in the update that you want to deploy. So delta updates are something that Mender supports. It can be fine-tuned in some ways. Beyond that, I don't think that there is a lot of knobs that you can use. One of the techniques that people sometimes use are modifying or tuning the update process in a way so it only relies on cellular if there is completely no other way, but can use Wi-Fi or cheaper communications if they are available, just like a mobile or a boat or an airplane or whatever. They will be expensive if they're flying and sailing, but cheap if they're in harbor or at the airport. And this is something that you can tune your update process.
Okay. Do you have a recommended best practice of extended poking in brackets and using remove overrides to take out stuff that isn't needed versus building from scratch with open embedded core?
I'll try and answer this, but I'm not sure if I fully follow if I've got the right end of the question or not. So you'll typically end up with your BB image, sorry, your recipe, your BB file, which is going to be for your image, will only include the packages that you require, and then BitBake will deal with all of the and the recipes will deal with all of the dependencies between other packages for you. Sometimes they have to be specific. The other recipes will specifically include the dependencies, both runtime and build time. Other time that's kind of automatic. But when you fundamentally, when you put the packages that you want into your BB image file, it will deal with all of just the requirement, just the dependency tree for those. So you shouldn't have to remove lots of things particularly, because you'll only end up with it including the things that you need anyway.
We've just had the guys just wrote saying, the guy or lady obviously, just says clarification of the last question, making one's own distro from scratch versus extending Pokey.
Well, just a short throw in from my side. I usually have a distro layer, which I base directly off Pocky. So I copy over Pocky, strip it of all the things that I need. So I essentially use the core bits of Pocky that I want, but I do not serve on the original Pocky because that might bring strange effects over release upgrades. So my technique is basing off, not exactly from scratch, but then carrying it myself.
Okay. Another question here. I have proprietary distribution. It is not destined to be shared. It's not designed to be shared, only for internal use. Should I split BSP specificities and distro specificities in different layers, or is it overkill for my use case?
Clear, yes, you should.
Yeah, it's so lightweight to create another layer that it's really not any hardship. Just do it. I
love a question when you both come. Yes, you should make a new layer. That's grand. Okay, when creating a BP appended file, does one have to use the same relative path to store the file within the higher priority layer?
So that's common convention, yeah. I don't know. I haven't done anything any different, to be honest. So just because it is common convention, but I suspect that it would be okay because it will just search there's basically a variable that contains a search path for all of the recipes and the recipe append files, and it should just match the name of the recipe plus any wildcarding on the version numbers, etc. But yeah, typically they'll be in the same named like recipe groups.
Perfectly correct. One extension, if you are doing dynamic layers, which means that you kick in specific appends only if another layer is actually active, then you will probably not carry the whole tree substructure in your conditionals. So then you just slap them into one collective or whatever. But as Nick already said, it is a good convention to stick to the original path so you can relate, but it is not needed because it's a pattern match on the file name.
Okay, great. And then the final question that we have here is, it's asking for an example, but maybe we can talk around it instead. So it asks, do you have an example where you can tweak machine overrides to break a collection of machines into subclasses and an override variable based on subclass? And it says, I know I did this a few years ago. I had 3 PowerPC targets, but 2 were so similar. I wanted them to have the same override.
Old man, PowerPC. It's okay. I actually have an example. It's done in both the Raspberry Pi and the Meta Freescale layers. They use mechanisms that are really, really similar to this. So I would suggest to look at those.
Okay.
And say hello to PowerPC for me.
Okay, there is actually one more. People just want one more, they're saying. Okay, so someone's asked, I've noticed that Mender does, oh, sorry, Nick, were you going to go in?
I was just going to say, just while we were talking on that last question, don't want to kind of overly confuse things, but just a couple of points. If you're using an old version of Yocto, so like before version 3.4 Honister, then the colons were underscores. So if you see lots of kind of underscore prepend appends and stuff, and you're like, well, this is different. That's just, like, and you're in an old version, that's why. And there was lots of syntax confusion going on with it, which is part of the reason why they changed it to a colon. And there's still lots of weird and wonderful other corner cases, which leads me on to my next bit, which I guess is that you can also have overrides for other things than machines and distros. So you can like override almost anything if you want by extending the overrides variable. And it's quite commonly used to do things like for the instruction set architecture. So you might end up with some conditional things which are like some conditional variable modification based on it being ARM versus x86, or you can override even particular packages and things like that. So you could insert extra packages into your recipe, for instance.
Okay, thanks. Oh, this one, Joseph, is for you because it's about Mender. So someone's asked, I've noticed that Mender does support using read-only rootfs partitions. Do you have a recommended resource for the checklist of what to change to make sure nothing tries to write to it?
Checklist is first, add read-only rootfs to the distro features, because that instructs Yocto to make the rootfs read-only. Checklist step number 2, run it and see what fails, because that will fall over if it tries to write to write-protected root file system, and will tell you what you need to additionally change. Usually this can be things in your application or middleware that you are using. So I obviously can't give an exhaustive list, because the list would be check for whatever writes. And therefore I say, make it non-writable and see what breaks.
That's how I live my life.
You see what breaks. Awesome.
Amazing. Thank you everyone for your questions. If I've missed any, we'll get back to you on email. Obviously our contact details are up here, so if you've got any other questions for Witekio or for Mender, then please do contact us, and hopefully we'll see you for Yocto Masterclass Part 3 some point in the future. Thank you, Joseph. Thank you, Nick.
Thanks, everybody.
Thanks for having me.
Bye, guys. Have a good night. Bye.
Have a good day.
Bye-bye.